All right, so at the end of the last lesson in UA5, I wrote down this two-column proof of the vertical angle theorem. So essentially I just said how we know that y and w have the same measure through a series of statements that we could back up with some reason. Okay, and so this is what's called the two-column proof. And the idea is we're using deductive reasoning, a logical argument that's based on facts to reach a conclusion. And so in this set of notes, UA6, what I've got here is, for the most part, the postulates, theorems, definitions, and properties that you're going to use as reasons for your statements. And often when we write proofs, the statements come somewhat naturally. That's the how you're going to do the problem, but this is the why. And sometimes that's a little bit harder. And so all I did was try to compile all the whys into one set of notes, because with very few exceptions, every justification that we use is either going to be a postulate, theorem, definition, or a property. So we haven't formally defined a postulate or a theorem yet, but we can say that both postulates and theorems are just statements of geometrical truth. Okay, so a postulate is a statement of geometrical truth, but it's assumed to be true. In other words, it's such a simple idea that it doesn't have to be proved in order to be believed. And here are some postulates that we've already learned. Here's a few that we didn't name, that if you have a line, it has to go through at least 2 points, or kind of the converse of that. If there's 2 points, there's exactly one line that goes between them. Those are ideas that are very simple. They don't need to be proved in order to be believed, but they're kind of the building blocks that everything else is based on. And we also have the corresponding angles postulate, the angle addition postulate, and the segment addition postulate. These are, kind of simple ideas that don't need to be proved. As opposed to a theorem. A theorem is also a statement of geometrical truth that must be proven to be true based on postulates or already proven theorems. So, in other words, they're more complicated, and so you can't just say, well, clearly these two angles are congruent without some kind of a justification. And so here are a few theorems that we've already learned: triangle exterior angle theorem, triangle angle sum theorem, vertical angle theorem, alternate interior angles, alternate exterior angles, and consecutive interior angles, and the base angle theorem. Okay, this is by no means a complete list. We're going to keep adding to this list, but so far these are the ones we're going to use. Okay, we're also going to use definitions in our proofs. Like, how do you know something's true? Well, by definition, we know that in this case, let's say, supplementary angles add to 180. By definition, that's what they are. And so again, here's just a short list of terms that we can use. And again, it's not a complete list, but these are things that are going to come up kind of, routinely. And I'll show you an example how they're used. But these, in a proof, you're going to write down in the justification column by definition of linear pair or definition of supplementary angle. Okay, and so you should know those. And then the last type of justification are properties. Okay, so a property is just an attribute, quality, or characteristic of something. In other words, or an example, addition. Addition has the property of being commutative. Subtraction doesn't have that property. Remember, commutative means that you can do something in any order, right? So addition has that property. So you can do A plus B, and that's the same thing as B plus A. Multiplication also has that property. A times B is the same thing as B times A. Subtraction and division don't have that property. So we're not going to write those here, right? 5 minus 3 is not the same thing as 3 minus 5. The associated property works with addition, meaning addition has the property of being able to regroup and get the same answer. So you can start with the group of A plus B and then add C, or you can start let's say with A, and then add the group B plus C. And it also works for multiplication. But these are old properties that you should be familiar with. You don't need to write down everything. Distributed property, right? A times B plus C is equal to AB plus AC. So in other words, if in one of your steps of your proof you have to do some algebra, right? You just back up that statement by saying, how do you know this is true? Well, that's the distributed property. That's how I know. Okay, we have the identity property. Again, this is one that you learned early on in algebra, and it looked like this, A plus 0 is equal to A. Or A times 1 is equal to A. What do you add to something to keep its identity, or what do you multiply something by to keep its identity? And even now that may look not that useful, but let me just give you a real quick explanation of why it is. If you have like x plus 3 equals 7, okay, we know that you're going to just subtract 3 from both sides. That's kind of the standard step, subtract 3 from both sides. Okay, but let me rewrite this kind of horizontally. X plus 3 minus 3 is equal to 7 minus 3. All I did is just rewrite that statement horizontally. Okay, well, this is an algebraic equation. Suppose this minus 3 was actually on the same side as that minus 3. Meaning basically, if we just put it over here, if it's minus on the right side, it's positive on the left side. So that means we'd have an x plus 3 minus 3 plus 3 equals 7. Okay, so we just moved the negative 3 over. So look, what did we actually add to this equation when we subtracted 3 from both sides? We actually added 0. Right, this is x plus 3 plus 0 equals 7. So in other words, when you add 0 to something, it doesn't change what it is. And so by doing this, we're really just adding 0 to the equation. That's how we solve. Okay, but this is all kind of like behind the scenes. We don't actually ever see this. But that's an example of what the identity property is. And the same thing's true for multiplication when you have something like 3x equals 9. You divide both sides by 3. But suppose this 3 were put back on the other side. Well, you'd have 3 divided by 3, which is 1. So we're just solving this equation by multiplying by 1. Okay, a little off track. That is okay. Let's come back. The addition property of equality, you can add something to both sides of an equation, and it maintains the equality. So A plus C is equal to B plus C. Right? If you start with A equals B, you can add C to both sides. If you start with A equals B, you can subtract C from both sides. If you start with A equals B, you can multiply both sides by C. Make both sides C times bigger. Okay, in division, if you start with A equals B, you can make both sides C times smaller, or divide by C, as long as you're not dividing by 0. Okay, so those are all old, and may have forgotten, but that's something you learned in Algebra 1. But here's a few new ones. Okay, reflexive property of equality and reflexive property of congruence. All it means is that anything is always equal to itself or congruent to itself. So, a length is equal to a length, or an angle is equal to an angle, or congruent to itself. Simple idea, but it's going to show up and be useful. The symmetric property of equality, right? Equality has the property of being symmetric. Okay, so that means if A equals B, then B equals A. It's symmetric. And the same thing is true with congruence. If, let's say, angle B is congruent to angle C, then angle C is congruent to angle B. Right? Simple ideas. Transitive property. Well, this root word is transit, so like a bus going from station to station to station. If A equals B and B is equal to C, then what's a logical conclusion you can make if these two things are true? A goes to B and B goes to C, then A goes to C. All right, so that's the transitive property of equality, and it holds true with congruence. If angle A is congruent to angle B, and angle B is congruent to angle C, then angle A is congruent to angle C. All right, and then the last one is actually one that you've used before, whether or not you've actually written it down, is the substitution property. And it works with equality or congruence. I'm just going to write an equality example here. But the idea is, if A and B are the same, if A and B are equal, then B can replace A in any expression. All right, let's go now to how we're going to apply it. Okay, so we're going to apply these ideas. We're going to write them down in what are called two-column proofs. This says we're given some information and we're trying to prove this. Okay, so we have this diagram. That's part of the given information. And when we write a proof, right, you have to kind of think, where are we starting? Where do we need to end up? And we need to develop a plan to get from A to B. So what I like to do is just start out by labeling what we know to be true. 4 and 3 are congruent. And C is parallel to D. So we write that down. Okay. We also need to kind of keep in mind, just from the diagram itself, what do we know is true? Okay, so I'm going to do that in a different color. Well, we know 1 and 2 are the same measure because they're vertical. And since these lines are parallel, we also know that 1 and 3 are the same measure because they're alternate interior. Okay, so just things that I know to be true. This is how I do a proof. And really, I would probably do this somewhere else, not right above it, but just some scratch work. We know, and again, I'm going to be very kind of sloppy here. 4 is equal to 3, right? I'm not going to be too formal. But we know 4 and 3 are the same measure. We know 3 and 1 are the same measure. We know 1 and 2 are the same measure. Okay, so these are just things we know. Now keep in mind what we're trying to prove. We're trying to show that 4 and 2 are the same. Well, we know 4 and 3 are the same, and 3 and 1 are the same. Therefore, 4 and 1 are the same. And then we also know that 1 and 2 are the same. So that means we can replace this 1 with a 4, right? Use substitution. So we kind of come up with a plan, then we write it down here formally in statements and reasons, how we know. And you typically start a proof with what you're given. So we know that angle 4 is congruent to angle 3, and C is parallel to D, and that's given. It's okay to use all your given information here if it's necessary for the next step. Otherwise, you can hold off and use it later. But typically, you write your statements in the order that you're using the information. You don't just write everything at once or in random order. You kind of write it in a logical sequence, right? We started with this. So our next statement was, well, if we know 4 and 3 are the same, we also know that 3 and 1 are the same. Okay, so here we're going to write it a little bit more formally, right? Angle 3 is congruent to angle 1. And now we give our reason for knowing that. And that's because the alternate interior angle theorem. Okay, so it's okay to abbreviate, well, at least especially here, we don't have a lot of room. Okay, statement 3. We also now know that if 4 goes to 3 and 3 goes to 1, okay, the next kind of a logical statement, kind of a conclusion, or if we followed this idea, would be that 4 is congruent to 1, right? 4 goes to 3, 3 goes to 1, so therefore 4 goes to 1. So angle 4 is congruent to angle 1. Well, how do we know that if 4 goes to 3 and 3 goes to 1? That's the transitive property. And because we're dealing with congruence, we're going to say transitive property of congruence, PC. If we're dealing with equality, then we say PE. All right, statement number 4. What else do we know to be true? Well, we said 1 and 2, is part of our problem here. We need to show that 1 and 2 are the same measure. Okay, so angle 1 is congruent to angle 2, and that's because of the vertical angle theorem. Okay, and as you're doing this, and you should already have a plan, but just keep in mind that we're trying to get to 4 and 2 are the same. Well, we have 4 and 1 are the same, and 1 and 2 are the same. So if 4 goes to 1 and 1 goes to 2, then 4 goes to 2. 4 and 2 are congruent. Notice that's what we were trying to prove. And the reason is, well, we just used the transitive property a second time. All right, so the idea is we have proven without a doubt, right? We've used deductive reasoning. We used facts to prove that 4 and 2 have to be the same measure. And because it's clearly written in a sequential order, like a logical argument, we've proven that 4 and 2 have to be the same. And at the end, we either can write kind of a large period, a square period sometimes, or you can write QED. It's like a Latin phrase, which was to be proved. But either way, you just kind of say, all right, my proof is finished. And just keep in mind that your last statement should always be what you were trying to prove, right? The last thing you write is this. All right, we'll do one more together. You try a couple on your own, and we'll see how you do. All right, number 2. We're given that these two lines are parallel, and we're trying to prove that these two consecutive interior angles are supplementary. Okay, that should be familiar. This is just the consecutive interior angle theorem that we're proving. Okay, so we can't say we know these are supplementary because of the consecutive interior angle theorem. Right? We're trying to prove that theorem, so we can't use it in the proof. But like before, I like to write down, kind of label what we know. We know the two lines are parallel, so we can use other theorems, though, to prove the consecutive interior angle theorem. But keep in mind, we need to be using angles 6 and 3 somehow. And right now, we don't know that 6 and 3 add up to 180, but we do know 3 and 2 add up to 180. Right? That's just something we know. And I'm trying to keep 3 in the picture. Okay, so 3 and 2 add up to 180. And I'm just going to say that, again, just kind of a scratch word. All right, 3 plus 2 equals 180. That's something we know. Since these lines are parallel, we also know that 2 and 6 are the same measure. 2 equals 6. Keep in mind, we're trying to show that 3 plus 6 equals 180, right? The measure of angle 3 plus the measure of angle 6. Well, this says 3 plus 2 is 180, and we know 2 and 6 are the same, so we can replace that 2 with a 6. Substitution. Okay, so there's kind of the flow, the sequence that we're going to work through. We just need to formally write it out, starting with our given L is parallel to N, and that's given. All right, statement 2. Again, so the proofs can be sometimes difficult because there's not any kind of pattern to follow like an equation. Move all the variables to one side and everything else to the other side, something like that. You have to really plan it out, and they're all different. And 3 and 2 didn't say anything that we had to use it. We just kind of said, well, let's use 3 and 2 and use that in our proof. So we started with the idea that, hey, we know 2 and 3 are supplementary. Let's use that fact. So we'll write that. Angle 2 and angle 3 are supplementary. Sorry, I didn't leave a lot of room. And our reason for knowing that is a definition. What kind of angles are they? They're a linear pair. So by definition of linear pair, we know those two angles are supplementary. Okay. Next logical statement. Therefore, if these are supplementary, we know the measure of angle 2 plus the measure of angle 3 is 180 degrees. Well, how do we know supplementary angles add up to 180 degrees? Because that's how they're defined. So by definition of supplementary angles. Okay, so now we have 2 and 3 add to 180. That was kind of our first idea. Statement 4 was that angle 2 is congruent to angle 6. Or let's just say actually I'm going to do this just so you see what happens when it occurs. But I'm going to write this as a congruent statement instead of equality. I'm going to say angle 2 is congruent to angle 6. Well, how do we know that? How do we know these corresponding angles are congruent? Because of the corresponding angles postulate. Now keep in mind I did this on purpose, but we wrote a statement that's in congruence, and our final statement is in equality, so we have to kind of make that jump from congruence to equality. So if these two angles are congruent, then their measures have to be equal. And how do we know that they're equal if their measures are equal if the angles are congruent? By definition of congruence. All right, one more step, we're almost done. Last statement. 2 plus 3 is 180, and 2 and 6 are the same. Well, therefore, we can replace that 2 with 6 and get the statement 6 plus 3 is 180, which is what we're trying to prove. Okay, so we're going to replace the 2 with a 6. That's substitution. So now the measure of angle 6 plus the measure of angle 3 equals 180 degrees. Remember, it doesn't matter the order that we write it, because addition has the property of being commutative. So this is what we're trying to prove, and how did we know that? The substitution property. Okay, so this last statement matches what we're trying to prove. Everything follows sequentially in a logical argument, and that's our proof. All right, so work together. You've got 2 examples here to work through. I'll leave the key here so you can check them, and then go ahead and move on to the practice that I've given you. All right, thanks a lot.